Well, thank you very much for the invitation. So I wanted to tell a story about relations between topological field theory and the geometric Langlands correspondence, or if you like, in geometric representation theory. And this story, I think, begins in 2006 with a paper of Kapustin and Witten called Electric-Magnetic Duality in the Geometric Langlands Correspondence, where Kapustin and Witten explained how to see a lot of the structure of the geometric Langlands correspondence from something called n equals 4 super Yang-Mills in 4 dimensions. So this is a 4-dimensional supersymmetric quantum field theory, specific one called n equals 4 super Yang-Mills, which we might say a little bit more about later. And they explained how to see a lot of the structures of geometric Langlands. And since then, the kind of level of sophistication of the interaction between physics and geometric representation theory has kind of grown quite a bit. And what one can now see a lot of the things that we are interested in geometric representation theory out of structures in the physics. So my goal in these talks is to try to explain some of this. So these are going to be math talks, not physics talks. So I'm not going to explain exactly what n equals 4 super Yang-Mills is or what the process is. I'd like to see some of the structures we know from geometric representation theory out of the physics. So now, maybe I want to start with some kind of claim. So the claim is that you can see a lot of, you can see the usual kind of the Rham geometric Langlands correspondence of Balance and Drinfeld and Rinken gate square. You can see a lot of that structure out of the physics. But you have to go up to 6 dimensions, and maybe to say a disclaimer. So we're not going to get there. We're going to make it up to perhaps 4, which is where the original Kapustin-Witten story, and we're going to see kind of toy versions or simplified versions of a lot of the structures that are of interest in geometric Langlands program. What we're going to try to do is try to build mathematical models of field theories that capture some of these structures using a very wonderful tool we have, which is the Cobordism Hypothesis. So I will try to explain how we can build some models for some of these structures using topological field theory. And today we don't yet know how to get up to 6 in this kind of model building approach. But I'd be happy to discuss a little bit about that at some other point. In any case, let me to get started. So I'm going to be talking about topological field theory from the point of view of Jacob Lurie's work on the Cobordism hypothesis. So what is a topological field theory? Topological field theory is going to be a representation of a higher category that's built out of Cobordisms of manifolds. So we're going to start with some higher category made out of Cobordisms of manifolds, and we're going to try to represent it somewhere. So let me give the kind of schematics of this. So there's some object called board N, and there's actually a few versions. So let's say there's going to be a few versions with adjectives like framed or oriented or unoriented or spin, various adjectives we can put on the kind of manifolds. And this is going to be a symmetric monoidal higher category. So it's going to be an infinity N category. And I will treat these things in a very kind of schematic way. So let me say schematically, what kind of thing does this look like? So first of all, it has what are the objects? So the objects of this category are going to be points, so zero manifolds. But the way they remember this structure and so I take this zero manifold and I make it, give it a frame, I give it an n-dimensional tangent bundle. So I look at the stable n-dimensional tangent bundle. So just look at a trivial rank n bundle over this zero manifold. And I'm going to give this some tangential structure, on this n-dimensional stable tangent bundle. So in other words, I'm going to be looking at, for example, if I look at a framed field theory, I just take the n-dimensional trivial vector space, framed vector space at each of these points. So it's some zero manifold, but then I think of them as having an n-dimensional tangent bundle, give some structure on that. Now, what are my one morphisms? So one morphism between two things. So it's going to be a one manifold. That's a cobordism. So if I have two zero manifolds, I can look at a one manifold. That's a cobordism between these. And again, I'm going to be thinking of everything inside as having an n-dimensional tangent bundle. So I just stabilize the tangent bundle of this n manifold to get an n-dimensional tangent bundle and give it whatever kind of structure, framed, oriented, or spin, or whatever it is, as an n manifold. So that's the structure of the Cobordisms. So for example, if I look at endomorphisms of the empty zero manifold, these are going to be closed one manifolds. So inside I have closed one manifolds with whatever structure appearing as maps from no zero manifold to no zero manifold. So now I can look at two morphisms, and two morphisms are going to be Cobordisms between Cobordisms, so pictures like this. So Cobordisms with corners between these two manifolds with boundaries. So if I have two one morphisms, I can talk about a Cobordism between them. That's the kind of objects I'm going to have as two morphisms. In particular, I can see closed two manifolds appearing this way. Again, it's endomorphisms of kind of an empty set. And so on and so forth. So this is so the idea is that I keep going up and up, and I look at Cobordisms between Cobordisms until I get to the top. And what makes this an infinity in a category? When I look at the collection of n morphisms, I'm going to think of classifying spaces. At the top, I'm going to have classifying spaces of Cobordisms, or if I want to think more categorically, their fundamental infinity groupoids. So infinity n category means I have morphisms going all the way up. I have morphisms for every degree, but everything above degree n is going to be just invertible. So one way to summarize that is to say that in degree n morphisms, rather than having a set of morphisms, I have a space of morphisms, a homotopy type of morphisms. I'm going to use the word space or homotopy type or infinity groupoid interchangeably. So I have the collection of all the invertible morphisms in degree bigger than n is going to be summarized in just giving a space. And the point about these space is let's just give and just to make this a little more concrete. So if I look at, so for example, two Cobordisms, and look in board 2 and look at oriented maps between the empty one manifold and the empty one manifold. What kind of thing is this? We're looking at closed two manifolds, oriented closed two manifolds. So they're mapping from an empty one manifold to empty one manifold, so just closed two manifolds. But there's a lot of closed two manifolds. So this is a disjoint union over the genus of the space of closed two manifolds of that given topological type. So this is a union of classifying spaces of diffeomorphism groups of surfaces of oriented surface of various genus. So we get this topological space, or if you like, this is just the classifying spaces of the mapping class group in genus bigger than 1. We're just getting the mapping class group, or the moduli spaces of curves, appearing as the spaces of morphisms in here. OK, so that's the rough kind of structure of this category. So I'm going to remember families of Cobordisms. In other words, I'm going to remember the topology of the spaces of Cobordisms. Yeah.
These are just the two maps, right? Not the whole category.
Well, I'm going to think of this is all the maps of, there's a maps in board 2 from this. This is the maps between the empties. This is sort of the part of this given by closed 2 manifolds, so I can think of them as maps from the empty 1 manifold, or if you like, the empty endomorphisms of the empty 0 manifold. And so I have, and the point is that I'm not going to get sets of objects. At the top level, I'm going to get spaces of morphisms. And the spaces are always going to be classifying spaces of different morphism groups. Okay. Okay. So so I'm not going to spell out. So to make this into a category, there's a lot of structure, but roughly, very schematically, the composition is given by gluing. So if I want to compose some boardism with some other boardism, so I'm sure everyone has seen lots of pictures like this. I'm going to glue them, and I have the tangential structure along the boundary to enable me to make this gluing. So the composition is basically taking gluing over common boundary pieces. So that's sort of the caricature, and the symmetric monoidal structure. Well, there's a natural operation you can do on these boardisms, which is disjoint union. Okay. So, yeah.
Once you also have stripes, like, as your...
I mean, sorry?
You have circles here, yeah, totally. But if you don't do with, instead of empty...
Yeah, so I can also have pictures with corners where I have, yeah. I don't know. Something like that. Okay, so I'm going to treat this very schematically, and the point is we're going to, how does this boarding work? No, I see. There's some, okay, something like that. All right, so we'll see. So this is we're taking this as a black box, and that point is going to be to spell out some of the structures that are encoded in this machine. So the definition of an n-dimensional topological field theory is going to be just a representation of this boardism category. So I have a category of n boardism, and I can talk some class, say framed or oriented or whatever class of n boardism, and I just want a functor. It's going to be a symmetric monoidal functor, so a representation of the structure I have into something of the same kind, into some other infinite symmetric monoidal infinity n category. So it's just a map like this. So we'll specify what kind of targets we want to. But before we say anything about where do we want to represent this, I wanted to state the main theorem that we're going to be using as to build topological field theory. And the theorem, there was a conjecture of this is a conjecture of Bayes and Dolan and a theorem of Jacob Lurie. And what this theorem says is that it classifies these things. In other words, it gives I'm not saying anything about what the target is, so we're really going to give a universal property of the source. So the source has this very nice universal property. It says that if I look at, and I'm going to look at framed topological field theories, so all my n manifolds will have trivializations of their tangent bundle. So if you look at framed n-dimensional topological field theories, so framed n-dimensional topological field theories are completely determined by certain objects called n-dualizable, given n-dualizable objects of the target. So to any, where to a topological field theory Z, I'm going to attach Z of the point with a trivial n-dimensional tangent bundle. That gives me an object of here that's going to have some properties. Given an object of C with this property, which I'll say a little bit about in a second, that completely determines the field theory. So given an object, let's call this A. Given an A, we can construct a topological field theory, which I'm going to denote schematically as taking any manifold M, and the output I'll just call the integral over M of A. So the integral over M of A is a notation here for the Cobordism hypothesis. Given an input that satisfies some finiteness condition, there's an integration procedure given by this theorem that says that you can integrate this on any framed n-manifold with corners that you want. And this is not at all an explicit operation. It's something that's just a way. So this notation is just sort of to paraphrase. It's just a paraphrase of this theorem. And now, right. So now what do I do? I can't do two at once. Okay, so let's see what. So that's now. Let's say a little bit about what dualizable means, and then we'll talk about various extensions. So this is kind of the bare bones version of the Cobordism hypothesis, and we're going to have various more elaborate versions we're going to use. But this is no.
So, David.
Yes.
There's a secret to Cobordisms. The top is the front. The top bottom is the front.
I'm framed here, so I'm a little, yeah. Okay, thank you. Disoriented. Okay, so what is the, okay, so what does that mean to be dualizable? So dualizable means it has duals in an n-dimensional sense. So being an n-dualizable object means it has n-dimensional duals. So what does it mean? First of all, what does it mean to be dualizable? So what does it mean to be a dualizable object? And for this, we just need of a symmetric monoidal category, or infinity one category. And one thing that's very useful about this world of infinity n categories is I can always forget down. An infinity n category means I have a whole bunch of invertible morphisms going all the way up, and I have non-invertible morphisms in degree up to n. But I can always forget some of those. So an infinity n category I can always think of as an infinity 1 category, where I just forget every morphism above degree 1 that's not invertible. So it still goes all the way up, it just only have invertible morphism above degree 1. Okay, so what does it mean, a dualizable object? So dualizable object means I have an object V. Given an object V, we say it's dualizable if there exists some object, which we'll call V dual, together with maps, together with a map from the unit to V tensor V dual, which we'll call eta. This is the co-evaluation, and a map epsilon from V tensor V dual to 1. This is the evaluation. And these two maps satisfy a relation, which is the Markov-Zorro. It says that if I give you a map, I can look at a map from V tensor V dual to V, and this is the identity map from V to V, where these maps here, this is going to be epsilon, and this is eta. So I have this kind of relation, so this is the notion of a dualizable object. And so, for example, I don't know if did this appear in the talks already? Probably did. But so, for example, a vector space V, a usual vector space is dualizable if and only if it's finite dimensional. Finite dimensional, and V dual is the dual vector space. So this is the notion of a dualizable object. And now we want to lift if now we're saying, suppose you're not just in an infinity 1 category, you're in an infinity 2 category, then you can ask to have duals also. Oh my, now we have to do this thing again. Yes. So if you're in higher dimension, you can now ask for not just the objects to have duals, but you want the objects to have duals in a category where you restrict the one morphisms. So I can ask in an infinity 2 category, I can ask also for eta and epsilon. If I have enough room to ask this question, I can ask for eta and epsilon to also have duals. duals, which means the notion of adjoints. So I have now room for morphisms between morphisms. So I can ask for a map, I give an eta, I can ask for an eta right with the usual adjunction properties, whatever. I have a 1 to eta right eta, and so on. Eta right to 1, satisfying the usual adjunction identities, which are literally the same picture as V goes to V tensor V dual. I'm now asking this about the one morphisms. And so if I can, so being two dualizable means I'm dualizable, but using adjointable, using only dualizable maps, dualizable etas and epsilons, and so on. So once I have a notion, so now if I'm in infinity 3 category, I can look for these maps, the adjunction data for eta and eta r, to also themselves have duals. And each time I can ask for more and more and more duals between, so I ask for my object to be dualizable in a world where I'm only allowing maps at every point that have duals themselves. So that's the notion of an n-dualizable object. And the Cobordism hypothesis says that frame topological field theory is uniquely determined by just giving such a single n-dualizable object of my category. Okay, so all right, so that's the bare bones Cobordism hypothesis. Maybe the next some variants. I'm going to be very not going to worry too much about framings versus orientations or so on, because there's a nice version that so from the Cobordism hypothesis, one gets that there's an action of the group ON on the collection of objects. So I look at this. There's a groupoid, an infinity groupoid, or a space, which is I look at just all the n-dualizable objects. Look at all the fully dualizable objects, and a fully dualizable object is the same as a topological field theory, a frame topological field theory by the theorem. But on frame topological field theory, I can change the framing. So this gives me an action of the group ON on this space. And so given any group G, any structure group G mapping to ON, for example, SON or spin N or your favorite group together with a map to ON, you can then get a corollary that says if you look at functors board N with G structure, if you want topological field theory on G manifolds to C are given by fixed points, I should say n dualizable by homotopy fixed points of G here, by invariance. So if I give you an n-dualizable object that's invariant under ON or under some subgroup of ON, I can talk about a field theory that's defined not just on frame manifold, but on manifolds with my favorite structure.
So an object at the start is a point plus a vector space plus a metric plus an orthogonal basis, or less than that?
It's a point plus a framing plus a basis of the n-dimensional tangent bundle. There are no metrics.
What do you mean by tangent bundle? It's just a vector space?
Yeah, it's a trivial. I mean, I'm taking my zero manifold and give it an n-dimensional tangent bundle, which is a trivial.
So the ON structure must come from a metric.
Well, it's a trivialization. I have framing. It's a framing of that n-dimensional tangent bundle. So I have a basis. Yeah, sorry. I see the ON versus GLN. Let's call it GLN.
Okay.
ON equals GLN. So here the group. I mean, the group here is we're asking this. This is a group acting on some homotopy type. So everything is happening on the world of home. So I'm thinking of ON just the home. So I can think of them as vector spaces with inner product. I'd rather not. Just think of this as GLN.
So can we write GLN?
Yes. Yeah. So this is a group in the homotopy homotopy world. Okay. So this is the bare bones of the Cobordism hypothesis. Now, one way to think about this is we can think of these conditions of a sequence of increasingly tough of finiteness conditions, so if I'm thinking about framed Bordism, finiteness conditions on an object, so if I give you an object V in some symmetrical monoidal infinity n category, I can ask for this object to be dualizable. I can ask for it to be 2 dualizable. I can ask for it to be 3 dualizable. I can ask to be 4 dualizable. I can ask, so I have this sequence of more and more tough finiteness conditions, which you can think of for the convergence. So I can think of these as convergence conditions, convergence of this operation, integral over M of V, on higher and higher dimensional, and increasingly higher dimensional manifolds M. So I can think of, I'm trying to extend my field theory from level of points to level of 1 manifold, to level of 2 manifolds, level of 3 manifolds. Each time I want to extend higher for my frame field theory, I'm going to need this object to have kind of stronger and stronger finiteness conditions. And if I started with an infinity n category, I can ask to go all the way to n. And we'll find out that that basically never happens in our examples, but I'll try to make that more precise. So so when I think about a topological field theory, I'm always going to have a certain kind of target in mind. So when I say a field theory to a physicist, the target C is not some random thing. It's something that's some C-linear. It lives in some C-linear world. So what's the target? The target that we're going to be interested in for topological field theories. The basic idea, the kind of the desideratum, is that at the top level, the invariant I attach to a closed n manifold should be a complex number. That's sort of my dream. If I have an n-dimensional field theory, I think of having an n manifold attaching a complex number. And that's the basic guideline. So in other words, you want that in this category C, if you look at these kind of endomorphisms of the kind of empty n-1 manifold, of this kind of unit, the n-1 unit, the unit endomorphism of the unit endomorphism of the unit endomorphism, blah, 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 of C, you should want this to be C. I.e., what this, to put it in some other words, C is kind of is an n-fold de-looping of the complex numbers. That's just a phrase for saying that at the n-morphisms, I want to have complex numbers. So what does this mean in practice? So for example, if I want n equals 1, so I want a category. So I want somewhere where my category, where my morphisms, my morphism unit are complex numbers. I can take the category of vector spaces. Category of complex vector spaces is such a category. The unit is the vector space C, and its endomorphisms are indeed complex numbers. Or we're going to be replaced vect by DG vector spaces. That's going to be the kind of setting I want it to be living in. And then I have when I talk about this, I have a choice of whether I want small things, finite dimensional vector spaces, or large. I have kind of small or large versions, or large versions of these categories of DG vector spaces. Say. I could look at perfect complexes, or I could look at all complexes. So they're very variants. There are more and more variants as I go up. So if I want dimension 2, one thing I could take, the kind of obvious guess I can take is just look at C-linear categories, or C-linear DG categories. At some point, probably now, I'm going to stop writing DG. So everything is sort of going to have DG or infinity in front of it somewhere. So you can think of just a category of complex linear categories. That's something that has C-linear, has vector space, C-linear vector space as its one morphism. So this is kind of a de-looping of this category. The endomorphisms of vect in here are vect. So that's one guess I could take, but there's something more pleasant in some ways. Rather than thinking about categories, there's a favorite kind of categories that we like, which is look at algebras. So instead of looking at a category, I can think of instead of categories, I can look at categories that have one object. So if I look at a category that has a single object, it's a C-linear category, then endomorphisms of this object form an associative algebra, or DG associative algebra A. So a category with one object gives me a DG algebra. But maybe rather than thinking of a category with one object, I can think of better, or I can think of as categories that are generated by one object. So in other words, both of these are versions of an associative algebra. So if you have an associative algebra, I can think of it either as a category with one object, or I could just look at the category of modules. So given an algebra A, I'm going to look at the category A mod, and that's going to be a DG category. And the category A mod is generated by a single object, so inside of the category. So given an associative algebra A, I look at the category A mod, and inside of here I have this distinguished object A, whose endomorphisms of this object are again A, or A up. So it's a category that's associated to this algebra. So in other words, when I think about categories, I usually look at categories that are modules for an algebra. And so I'm talking about looking at the Morita theory of algebras. So inside of the world of all categories, there's the simpler Morita world of algebras. And that's kind of another delooping of C. That's another good two category I'm going to be interested in. And now you can play this game. You can keep playing this game. Suppose you're trying to construct, yeah.
There's this old story n equals 2 that associates Frobenius algebras. How does that fit in?
So that's where we're not right. Well, I haven't said anything about field theories, right? Right now I'm just saying what kind of target I'm interested in. So the Frobenius algebra is going to come when I'm going to ask to give an oriented two-dimensional topological field theory. The target is going to have to be a finite-dimensional semi-simple Frobenius algebra if I'm not in the DG setting. But we'll say something about that later. But that's the Frobenius is going to be an orientation condition. It's this invariance for this group SON, SO2.
That's the symmetry property.
Yeah.
Symmetric Frobenius. But I mean, already if you're just in dualizability condition. Yeah,
I haven't set any conditions yet. I'm just saying what the target is. Yeah, we'll talk about that later. So in dimension 3, I have kind of a hierarchy of things I can take. For what kind of 3 categories am I interested in? And they get more and more concrete. So I can look, if I'm trying to construct a 3 category, I can talk about some notion of C-linear 2 categories. So something where the hums are C-linear categories. Or I can talk about algebras. So before I had I had 2 versions, I had categories and algebras. Here I could talk about algebras in C-linear categories. In other words, monoidal categories. If I look at monoidal C-linear categories, so these are associative algebras in here, or I can talk about algebras in C-linear vector spaces. So I have these kind of 3 different worlds. So this is what's a name for an E2 algebra. So we have this hierarchy. So what does this mean? We can look at all 2 categories, or we can look at 2 categories that are generated, or maybe let's just say 2 categories with only one object. So if I give you a 2 category with one object, then its endomorphisms form a monoidal category. Or I can look at a 2 category with one object and one morphism. So I look at kind of simpler and simpler categories. And such a category will be the same as an algebra in algebras in vector spaces. So what does this mean? It means a vector space with 2 associative algebra multiplications that are compatible. So you can think of this as an algebra that has a kind of a vertical multiplication and a horizontal multiplication. And they're compatible, and there's a theorem that you can find in Lurie's higher algebra that says that these 2 things, that such a thing is the same as an algebra over what we might have seen as an E2 algebra. It's algebra over the little 2-disk operad. In other words, once you allow yourself a kind of a vertical multiplication or horizontal multiplication, you might as well go crazy and allow any multiplication labeled by disks inside of a big disk. So anytime I give you two elements of algebra labeled by 2 points, 2 small disks inside of a big disk, I can define a multiplication. So I can realize them kind of vertical multiplication or horizontal multiplication, but I can also multiply them at any angle if I like. So we'll talk a little more about these. Yeah, that's right. So if you have two, so this is the usual trick of that. If you have a group, you have a set that has two group structures that distribute over each other, then the two group multiplications are A commutative and B equal. And this is exactly the structure. This is kind of the homotopical version of the structure. This is the picture you see if you look at this, how you prove that pi2 of a space is commutative. This is exactly the structure. This is the structure you get on a twofold based loops in a topological space. You get exactly this kind of commutative multiplication on the level of pi naught. This is just the abelian group, which is pi2 of x, but there's kind of a homotopical refinement of that structure. So but categorically, we could just think about this as a very special kind of two category. So there's a Morita theory. Among the world of two categories, there's kind of monoidal categories, or kind of simple two categories. And the simplest two categories are the ones that are just given by a single object and a single morphism, by just a single algebra. But the algebra needs to be this E2 algebra. Okay. And given an E2 algebra, if I give you an algebra A, well, we'll talk about this more later. You can talk about the two category. You can first look at A mod. You look at modules for this algebra, but because you still have an associated, you've used up one multiplication by looking at modules, this is still monoidal, and you can look at A mod mod. So given an E2 algebra A, 8 mod is a monoidal category, and A mod mod is a two category. Given a monoidal category C, we can look at C mod is a two category. So we're building up higher categories. So the point about this is that when we talk about higher categories, they're usually going to be much more explicit than just saying some three category. I'm usually just interested in giving a monoidal category or maybe an E2 algebra. So the field theories that we're going to build are going to be very concrete in our inputs. So to get to this geometric Langlands story, we need to go one more up. We need to go to n equals 4. We need some 4 category because we're going to be interested in building 4-dimensional field theories. And again, you have the same hierarchy. You could look at the 4 category of C-linear 3 categories, whatever that is, or monoidal 2 categories. That's a little more concrete. Or you can look, so these are algebras in 2 categories, so that's still not very concrete, but I can also look at algebras in categories, so an E2 category, and this is the same thing as a braided tensor category. So the next thing on the hierarchy is just a braided tensor category, which is something we are very familiar with in representation theory. So that's what fits in the next, and you can go one step more, and you look at algebras and algebras and algebras, which are these E3 algebras. So this is something with 3 compatible multiplications, or multiplication that's labeled by little spheres. Okay. So these are the kind of things we'd like to have as the targets of our field theory. So in practice, we're going to build 4-dimensional field theory, we're going to live somewhere like this. We're going to live with something relatively concrete as our target. And now, what's going to happen in practice is I'd like to use this labeling n. This is how I think of my dimension of the field theory. So if I have a field theory that lives here, I want to think of it as being 4-dimensional. But of course, nothing is telling me that a given object here is going to be 4-dualizable. And in fact, we'll find that the field theories that we build will basically never make it to the top. In practice, you sort of never get actual numbers at the top dimension, which, if you look carefully at the physics, is not what they were telling you to get anyway. You don't usually expect to actually get numbers. So we're going to need some kind of notation. So I'll say an object. So e.g., suppose C is a monoidal category. A monoidal category. So that's an example of a 3 of a two category, so it's something that lives in line n equals 3, we could say it's 2 plus 1 dualizable. So I'm going to use this kind of notation, this hybrid notation. The 2 plus 1 means I'm trying to get to dimension 3. The 2 is going to say in the Lurie definition. So I can have a notion of a 2 dualizable object here, but it's living in a 3 category. So I'm going to remember the dimension of the target by this notation. Does that make sense, what I mean here? It's 2 plus 1? Okay, so we'll see some examples of these very soon. So let's, before we see some examples, let's do some of the structures you can do with topological field theory. So how can you build topological field theories from other field theories? So one structure we can do is this board okay to use? Is people can? Okay. So one structure, one little easy game you can do is called compactification. Suppose I give you an n-dimensional topological field theory, and I give you a K-manifold. Then I can build a new topological field theory that I'll call Z sub n, which is going to be an n minus k dimensional topological field theory. And it's built by this stupid trick that I just define. I only look at manifolds of the form which are products. So I say Zn of m is Z of n times m. So I just look at the values of the field theory Z on n times lower dimensional manifolds. Okay? So that drops the dimension of the field theory. I'm only allowed to look at manifolds up to dimension n minus k in this trick. So that's a version of what physicists call compactification. Something more interesting that we can do is called dimensional reduction. And what's a dimensional reduction? This is a more interesting way to reduce the dimension of a field theory. So if you look at this field theory, if I have a topological field theory and I evaluate it on a manifold n, this output by construction carries an action of the diffeomorphism group of n. So I really have a family here. I think of n as a family over b diff n. So I have the kind of moduli space of things homotopic to n, things isotopic to n. So that's b diff n. I have a family over b diff n. So the value of this n naturally forms a family over b diff n, which means I have something with an action of diff n. So that's part of the structure of this field theory, that I have actions of diffeomorphism groups on my outputs. So one thing I could try to do is get rid of this action. So since it acts on z of n, it also acts of z of n cross m. So if I look at the values of this compactified field theory, they all carry actions. Everything in the field theory has this action of z of the diffeomorphism group. So I would like to define. Would like to get rid of this to take, let's call it the reduction Zn of m to be Z of n cross m, but just take invariance. I'd like to take invariance of diff n. However, nothing is promising me that this will form a field theory. The thing above formed a field theory for kind of silly reasons. But taking invariance is not a symmetric monoidal operation. It's not going to commute with all of my structure. So this doesn't literally form a well-defined field theory. Now, physicists have some way of getting around this, and a good mathematical kind of ansatz for what dimensional reduction is we're just define the reduced field theory, the dimensional reduction, by saying, well, we need to integrate over m z of n invariance. In other words, I'm going to take and define a new field theory which to a point, I'm just going to change the value on a point. This theory on a point, the compactified theory on a point attached z of n, we can take invariance of this, That's a well-defined object, and then I can try to integrate that. I'm not promising you how dualizable this is. I'm not promising you what manifold, how far this will get. But this is a way of trying. This is kind of a way of trying to realize something like this, and this is going to be our dimensionally reduced theory.
Okay.
I don't know. Bracket just to say, I'm going to put an overbar for the reduced theory. Yeah. Okay. So that's.
The definition depends on the cobordism.
Yeah, that's right. I'm going to use the Cobordism hypothesis as a way of building field theories. And since I have this kind of local way of building a field theory, I can just locally get rid of this extra symmetry. So a physicist will say that the compactified theory isn't really an n-k dimensional field theory. It also has this higher dimensional modes, and you want to take invariant modes on this direction. And this is one way of defining that. Okay. So let's. Before we talk about examples, so most of what I'd like to do this week is talk about a list of 3 or 4 examples and spell out some of their structure in some detail. Before I do that, I wanted to mention one more generalization. There's this wonderful generalization of the Cobordism hypothesis called the Cobordism hypothesis with singularities. So I'm not going to say the general case. We'll see other cases of it later this week. But I want to say, so the Cobordism hypothesis with singularities describes the universal properties of higher categories, of kind of Bordism categories, of spaces with singularities, of stratified spaces, of spaces with prescribed singularities. And it's kind of a very powerful generalization. I want to just do a special example of this. The first kind of example of the Cobordism hypothesis with singularities is to say, suppose C and D are n-dualizable objects. N-dualizable objects in some ambient world, one of the categories I had before. And suppose I give you a morphism, a map from C to D. You can ask, what can I do with a map of field theory? So if you ask now, so you say, well, if you ask for this map to be a map in the n-dualizable world, you'll find that this map has to be an isomorphism. If you restrict C and D, if you restrict all your maps to be all dualizable just by that junction level all the way up, you'll see that at the very top you'll get that you need adjoints at every point. At the very top level, you'll find you'll start building inverses. So if you really look for n-dualizable maps, there aren't any interesting ones. You only get a groupoid. But we can ask for this map to have weaker dualizability properties. So we can ask for phi to be k-dualizable. K-dualizable for some k less than n. We can look at maps between dualizable objects that don't have all the adjoints that you'd want all the way up, just some of the way up. So for example, I can look at what you might call a k-dualizable object of C, or let's say object of D, which means a map from the unit. Let me call a map from the unit to C. So if I'm thinking of C, I'm thinking of this as the two category of categories, then C is a category. So this is some category, and the unit here is the category vect. And this map is really determined by just this C-linear map is just given by giving a single object of this category. So the notion of object of a category you can think of as captured by a map from the unit to C. And so we can ask to give a map which itself is dualizable. So it's a map with adjoints all the way up to degree k. And the Cobordism hypothesis with singularity says that such things can be pictured as so it says that such maps from the unit to C are the target, again, of a field theory, that these are the same things, these maps from the unit to C, which are k-dualizable, are the same thing as what a physicist would call a local boundary condition. So I could say maybe local boundary condition for the topological field theory determined by C. So what does it mean, a boundary condition? That means we can extend the field theory defined by C we have a topological field theory defined by C to manifolds with boundaries. We're going to allow special boundaries that are labeled by this object V. So I'm going to draw this. Think of looking at manifolds. So I'm going to have a boundary component which is colored and labeled by this object V, and I may have, so I'm going to be able to extend my assignment to such things. So I can look at something like this, or I can look at something like this. So I have my usual manifolds with boundaries, and then I have special boundaries that are labeled by an object V. And that's what the Cobordism hypothesis tells you. So given an object of the category, you're now allowed to label components as long as the dimension of these has to be at most k. Okay, so this is, from the point of view of the Cobordism hypothesis, this is really, or from the point of view of physics, this is the meaning of what you attach to a point, which is this object C. So if I think I tell a physicist that I'm attaching a two category to a point in the field theory, what is the meaning of the two category? That two category is the collection of all local boundary conditions in my field theory. And an object of this two category is the kind of thing that defines a boundary condition in the field theory. In other words, it enables me to label components of the boundary. Maybe this becomes clearer if we look more generally. If I give you not just a map from the unit, but just a dualizable map, a k-dualizable map, in general, then this is what this is the same thing as a domain wall. Domain wall between the theories, between the field theories defined by C and D. So what is a domain wall? It means that we can define the theory. These are all ways to extend the definition of the theory. I can now define the theory on bipartite manifolds. So I look at a manifold, and I draw one half of it in one color, and the other half, I have another part of it in some other color, maybe with some boundaries, and I have a wall in between them. So we can now, given a manifold that's divided into two parts, one part I call purple with C, and the other part I call white, say, with D, we can now define invariants of such pictures. So we can extend the functor to such diagrams. So for example, if I just take my manifold to be, let's just do an example of what kind of structure we have. Suppose I just take a product. So here's my boundary. Here's my morphism. So here's my theory given by C. Here's my theory given by D. The boundary between them is given by phi. That's my domain wall. What does such a picture correspond to? This gives me a map from Z, from the one theory evaluated on this 2 torus, say, to the value, let's just call this n. I don't know. This is what n here, to the theory D divided by 2 torus. And this defines a map like this. So this part of the structure you get is maps from here to here between the values of the theories on manifolds of dimension up to k. And this map is automatically going to be diff n invariant, because this picture is diff n invariant. So we can such domain walls give you, for example, maps between the values of field theories. Okay, so this is some of the vocabulary that we'd like to use for field theories, and so let's now build some examples. Okay, any questions? Okay, so we'll try to build some examples of field theories, and start from dimension 1. Not going to be a lot to say in dimension 1. So as we already said, in dimension 1, if I think of V a vector space, for a vector space to be dualizable, it's equivalent for V to be finite dimensional. And then we have, if you have a finite dimensional vector space, you can write down maps. Well, there's the inclusion of the identity into endomorphisms of V. But because V is finite dimensional, I can write this as V tensor the dual vector space, and then I have the evaluation map to C. And these two maps are going to be my eta and my epsilon. That defines the duality data. And moreover, I can calculate from this, I get out of this a number, which is the composition of these two maps, and the morphism of the unit, which is just a number, which is just a dimension of V. So it's the trace of the identity of V. And that number is the value I get of the field theory on there's only one interesting framed one manifold, or well, really only one compact one manifold. I can write Z of the circle. I can calculate Z of the circle as Z, break the circle into two halves, and use the gluing data, and I write this composition as a map from the empty set to 2 points, and then a map from 2 points to empty set. This map is just going to be given by eta, and this is epsilon, to V tensor V dual. So Z of the circle is exactly the dimension of V. So that's the only interesting invariant in a one-dimensional field theory, is the value of the circle is the dimension. OK, so that's all I want to say about one-dimensional field theories. Now, what about two-dimensional field theories? So, so now I'm going to be thinking about C-linear categories, or more concretely, C-linear algebras. And what kind of questions can I ask about C-linear algebras, or DG algebras? And so if I give you, so here where n equals 2, so if A as an algebra is always, it's always one dualizable. So again, I'm thinking about this as being 1 plus 1. I'm thinking of it being an object in 2 category. It doesn't necessarily make it to 2 dimensions, but it's always one dualizable. Because I can always write, so what does it mean to say it's one dualizable? I need to write a map from the unit to A to something, and I claim the dual is just going to be the opposite algebra. So this is going to be the algebra. So I need to give you a morphism. But this needs to be a Morita morphism. I'm thinking about these algebras as stand-ins for their categories of modules. So I need to give you a functor from vect to A tensor A of bimodules, or I just need to give you a bimodule. I just take A. A itself is if you'd like, I can think of by passing to categories of module. A defines a functor from vect to A mod A up. Just take the one-dimensional vector space to A. And so that defines the co-evaluation. I also can use A to define the evaluation. So we always have these evaluation and co-evaluation maps for any associative algebra. And so that makes it one dualizable. And if you calculate the dimension of A, so what is the dimension of A in this sense? So the dimension where by definition I'm going to take the co-evaluation of the evaluation. Or it's going to be what I attach to the circle by the same picture. And what do I get? I get the composite of these two, which is A tensor, and I'm going to emphasize that everything is secretly happening in some DG world. So it's a derived tensor product of A with A as bimodules, which is the Hochschild chains of A. So that's the value of the field theory on the circle. If you want to be careful about framing, I'm really thinking about this as this is the circle with a cylinder framing. So I'm thinking about this as a 2D field theory. I need to give everything framings as a 2-manifold. And once you get to the level of the circle, you have several possible framings. So the framing that we're using is a framing that's compatible with this picture. It's just the product framing. Okay, so this is really Z of the cylinder. Okay, and so any algebra is one dualizable, and so similarly, if I have a category C, for example, if C is compactly generated, if I'm in the world of large categories, these are also so something like A mod. These are also going to be 1 plus 1 dualizable. But if I want to go further, if I want it to be 2-dualizable, I get something much, much harder. So to be 2-dualizable, I need some strong finiteness properties. So if I give you a DG category, and C says DG category, or an algebra, rather think of it as category, is 2-dualizable if and only if it satisfies two very strong conditions that says C is smooth and proper. So this, what does this mean? It means it looks like, so it looks like sheaves, like say quasi-coherent sheaves if I'm looking at on a variety X, where X is itself a smooth and proper variety. So how do you test, what does that mean that it looks like sheaves on a smooth and proper variety? I need to look at my evaluation and co-evaluation morphisms. I need them to have adjoints. And now my evaluation and co-evaluation are given by the diagonal bimodule. So I'm looking at this object A, which is a version of the diagonal. And so what this smooth and properness means, it means finiteness for the diagonal bimodule. In case of algebras, you look at A as a bimodule. And I need finiteness both in each homological degree and boundedness, cohomological boundedness. So I can bound the diagonal both in each degree and in total in cohomological degrees. And these are two different finiteness conditions that you get. So I'm giving this sort of short shrift because what we're going to see is that most of the field theory, so this is a condition that you get in order for the field theory to define numbers to two manifolds, in order to be 2-dualizable. Once we get beyond dimension 2, none of our theories are actually going to make it all the way to the top. None of them are going to make it to give numbers, so we're not actually going to be so interested in an n-dualizable thing. And fully, yeah. Yeah, so the notation 1 + 1 is just it's a bad notation. It's supposed to suggest that we're living in we're trying to build a 2-dimensional field theory. So we have this convention that I'm thinking of, the 1 + 1 is telling you the target. I'm thinking the target is C-linear categories. That's that 2-category target. But the first one is telling me how dualizable it is. So any algebra is 1-dualizable. But I'm thinking of it as an object of a 2-category.
So that one will not give you a 2-dimensional.
It will not, that's right. So any associative algebra gives you a field theory that's defined on 1 manifold, but it won't give you invariance for closed 2 manifolds. To give invariance for closed 2 manifolds, you need something very small. So say if you're non-derived, if you're just in a discrete, if you have a discrete algebra, you need it to be finite dimensional and separable, or finite dimensional semi-simple over C. So for an algebra, you need to be a finite dimensional. Sorry? For Frobenius is if I want an oriented field theory. So here I'm talking, so if I wanted oriented field theory, I need Frobenius. If I want a frame field theory, I need it just finite dimensional separable. Okay. So let's,
Why shouldn't it be semi-simple?
so you need it to be separable. You need the multiplication to be split.
I think it's finite dimensional and with finite homological dimension is enough.
Right, exactly.
You need A to have a finite resolutions.
Right.
It might not be projective, but
right. No, I mean, I'm saying in the discrete setting. In the discrete setting, you need it to be semi-simple over C. In the derived setting, you need. Yeah. That's only in the discrete setting. Right. Okay. So let me give. So there are two kinds of examples. So of this 2-dualizable, if X is indeed smooth and proper, and I take the category C, which is quasi-coherent on X, then that's what I'll call, this is the B model. The topological field theory is the version of the B model. Another example of the same kind is if G is a finite group, I can look at the category of representation. C is rep G, and this is some version of what you might call 2D Yang-Mills. because it's sort of the same kind of example. So these are the kind of examples of two-dimensional field theories we'd be interested in. So let me spell out a little what the 2D Yang-Mills theory looks like. So if G is finite, this is two-dualizable, and you can attach numbers to any surface. So if G is finite, and we take this category rep G, then you get a field theory which attaches to a closed surface. It just counts the number of local systems, of G local systems on sigma. So we have a topological surface. We can look at, so if log G sigma, if you like, this is what appeared in Bertrand's talk. It's the derived mapping space from sigma to BG, though here it's nothing very complicated. It's just a bunch of points with automorphism groups. So it's the stack of local systems. So this is just a bunch of points, each of them with some finite automorphism group, which is the stabilizer of that local system. And when I count the number of points, I have to count them with multiplicities. I have to keep track of the number of automorphisms. So that's the kind of invariant. More generally, if I give you a surface with boundary, so I have, suppose I have a surface, and I'm really, I guess, thinking now of the oriented theory. I can define operations. Okay. I can define operations using there's natural correspondences. I can look at local systems on incoming boundary and look at local systems on the outgoing boundary. Local systems on sigma have define a correspondence between these by restriction to each of the two boundaries. And I can just define an operation which is, let's call these pi in and pi out. And I have an operation which is pi out push forward of pi in pullback is an operation from what I attach to these one manifolds. So I need to tell you what to attach to these one manifolds. So it's Z. So this is defined a map from Z of del in to Z of del out, where this is just functions on G local systems on each boundary. So to a one manifold, I'm going to look at the vector space of functions on local systems. And to a two manifold, I get corresponds this way. Now, if I have a circle, so here I have log G of this circle is just local systems on S1. So log G on S1 is just G mod G. It's elements of G, and I'm using this funny notation to denote the adjoint quotient of G, the quotient of G by conjugation. So here I have functions on G mod G. So this just means functions on G mod G, which means class functions. So I have operations on class functions labeled by surfaces. That's the kind of operations that I get out of the field theory. So okay. So let's try to make it a little more structure to the theory. We have still in this case of 2D Yang-Mills, we have these notions of boundary conditions and domain walls. So what do those conditions correspond to in this finite group setting? So what are boundary conditions? So boundary conditions of the field theory, these are, as we said, these are maps from the unit to my category. These are just objects of my category, C, or in general, so if I look at A mod, these are just modules for my algebra A, or they're objects of the category C. So those are the possible boundary conditions. And for them to be one dualizable boundary conditions means that I have to have a compact object of C. So in the rep G case, my one dualizable boundary conditions are just going to be finite dimensional representations of the group. So given a representation of the group, it defines the local boundary condition. Now, what is this good for? So let's just see, what kind of pictures can you draw? Well, we don't have a lot of room to draw pictures. So for example, I can draw, here's one manifold I could draw. Suppose I give you a representation V. I can draw this. So I'm now attaching, I have a one manifold, and I have each of the boundary components labeled with V. This defines a vector space, which is just going to be endomorphisms of V. And I also get, this vector space also carries an algebra structure, because I can draw the following cobordism, where I label these boundary components by, I have this, so I write this two-dimensional cobordism where I have boundary components labeled by this V. That's the kind of picture that I'm allowed to define for this version of the Cobordism hypothesis. And that defines a multiplication, which you can easily see as associative on end V. So we see end V together with its composition as an associative algebra appearing this way. That's not so exciting. Something more interesting we can see is there's one more natural picture we can draw with something one-dualizable, which is we can draw a cylinder. So you have a cylinder, and let me draw a cylinder where I've labeled one component of the boundary by V and left the other one free. So what does this picture correspond to? It tells me that I have this picture gives for me an element. So here I've attached Z of S1, which we said in general was the Hochschild homology of my algebra, or in this case was just, in the case of a group, was just class functions. So for general algebra, we get Hochschild homology of A. Here we get class functions. And here I've attached a V. So this defines a class. This picture defines an element, which is the character of V. So given a compact object in the category of modules for an algebra A, or in particular given a finite dimensional representation of a group, I get an element of class functions, which is the character of the representation. So this is how field theory knows about characters. And maybe for future reference, note this picture is S1 invariant. There's not a lot of room for an S1 action, but the picture is is a spherically, rotational symmetric picture. So this gives you the definition of a character in the theory, or in the case of a B model. In the case of the B model, if I look at quasi-coherent sheaves on a variety X, and I calculate Z of S1, which is the Hochschild homology of my category, then by the Hochschild-Constant-Rosenberg theorem, I can calculate this as being differential forms on my variety X, or here, if X is not smooth, I need to put the cotangent complex here. Symmetric algebra of the shift cotangent complex. So this looks a lot like the Chern character. This is a lot like the place where the Chern character lives. Okay, but so this is where we get these characteristic classes here. So we'll get to maybe Chern character in a second. To really see Chern character, we need to put in the Rham differential. But let's see what else can we do with characters, so how do you construct boundary conditions? One way to construct a boundary condition in the case of representations is to give a subgroup. So suppose I give you a subgroup B of G. Subgroup maybe secretly I'm thinking something like the points of a Borel of a group, algebraic group defined over a finite field or something like that. But I'm just thinking of a subgroup of a finite group. So given a subgroup of a finite group, I can define a geometric boundary condition. So I can define, so I can consider G local systems with reductions to B along the boundaries. So I can define this kind of boundary condition that I want geometrically. I now have a space If I give you a picture like this, I can look at G local systems together with a reduction to B along this boundary. And so in that picture, so if that's the kind of boundary condition I get, then what we attach to an interval, you calculate what is the space of fields attached to an interval. That's, well, you look at G bundles on the interval with reductions to B at the two boundaries. That's just functions. Well, that space of fields is the double coset space of G of B mod B, which is the endomorphisms of the representation, of the induced representation functions on G mod B. And that's the algebra structure I see here. If you can see, yeah, so you get the endomorphisms of the representation appear naturally this way. So this is sort of where Hecke algebras will appear. And yeah, so one thing you can do with this is I can think of this boundary condition as defining a sub-field theory. So if I have a boundary condition that I like, I have this algebra H, I can look at the category H mod, category of modules for H. And so what is this? This means the category generated by this induced representations, by the induced representation inside of rep G. So look at the full subcategory generated by this representation. This is what you might call something like a unipotent principal series. So given what I want to say is that if you give a boundary condition, you can try to define a new field theory where you define a new field theory by replacing your original algebra or your original category by a piece of that category, by a full subcategory. So it's a piece of the theory seen by this boundary condition. So this is what in physics you would call a super selection sector. Sector of the theory. I can look not at the whole G theory, but the part of the G theory that's seen by a given boundary condition. Okay. Now, all right. So finally, I can also get the character. So if you calculate what the character is, you see the formula for the character of induced representation. Let me draw the same picture. What is the character of the induced representation? Well, let's look at this picture. So I'm looking at G local systems on the cylinder together with a reduction to B on one boundary component. So we're just literally going to linearize this picture. So what is that picture? You get the space B mod B, which is the same as a group element G and G, and a point in G mod B that fixed by G up to conjugation. So if you write down what local systems on the cylinder with a reduction to B on one boundary are, they're exactly the local system. Its monodromy is given by an element of the group up to conjugation, but we also need to give a flag along the boundary that's preserved by it. So this is the space of local systems on this. And it has a map to G mod G, where I just remember the monodromy. So this is a version of the Grothendieck-Springer resolution. So I can call this G tilde mod G. And I have this map, and this formula, the character formula, tells me that the character of the induced representation is just given by I take the function 1, so I look at functions on B mod B, and I go to functions on G mod G. Inside of here, I have the function 1, and I just push it forward along this map, and that's the character of the induced representation. So that's what reading out the field theory on this diagram gives you. So that's the Frobenius character formula. If we want to maybe beat this example to death, we can also think about domain walls in the same picture. Instead of thinking of point mod B on its own, I can think, suppose I have a picture like this. Suppose I have, so I have B is a subgroup of G with quotient T, for example. Then I can define a domain wall between the theory defined by T and the theory, this is the T theory, and this is the G theory, and the B defines a domain wall. And what does that domain wall mean? That domain wall is just the language for parabolic induction. So this domain wall means there's a functor from rep T, which is what the T field theory attaches to a point, to rep G, which is pull back and push forward. That's what this picture gives. And if I draw another manifold with another bipartite manifold, which is crossing with a circle, I get this picture. And that gives me the character map. I get a map from class functions on T to class functions on G, given by, again, pull back and push forward. And this, again, is the formula for characters of general induced representations. It's just literally pull back and push forward of local systems on this. OK, so this is the way the field theory sees the formulas for characters. And this is going to get more interesting as we get to higher dimensional field theories, where the same pictures will work, but they'll give us much more interesting character formulas and much more interesting correspondences. OK, so let's just let's talk a little bit more about, while we're still in this two-dimensional setting, about dimensional reduction. So there's not a whole lot of room to do dimensional reduction from 2 to 1. So if I want to do dimensional reduction, I only have dimensional reduction of this of the B model. So what is dimensional reduction? I want to go from this two-dimensional quantum field theory to something one-dimensional. So I'm going to have to reduce on the circle. The circle is the only thing I can only closed one manifold I have. So what does it mean to do dimensional reduction in a circle? That means I need to look at the value of the field theory on the circle. The value of the field theory on the circle was the Hochschild homology of my algebra A, or my Hochschild homology of my category, which in the B model case is this algebra of differential forms. In general, it's Hochschild homology of your associative algebra. And the topological field theory axioms tell me that on this space, I need to have an action of the group diff S1. So the group diff S1 has to act on the Hochschild chains, or this Gilbert complex. So what is that action? Well, diff S1 is homotopic to just S1. So I need to give you an action of S1. And what does that action look like? Well, it's going to factor through an action of chains on S1 on this vector space. What are chains on this one? This just looks like, what did I call it? This looks like a DGA which generated by some element B with square 0 and degree -1. So I'm a homotopical action of S1 on this vector space amounts to an action of the chains of S1 on this vector space. And that algebra is just giving me an element of degree -1. And what is that element going to be? Well, this is, in general, this is exactly the con B differential. So given any associative algebra, if you look at the Hochschild chains of an associative algebra, Kahn introduced this, Kahn and Figgin and Siggin, the structure of an extra differential. In this case, it's going to be the Rham differential. This is the non-commutative generalization of the Rham differential. So considering the S1 action here means considering the S1, the Rham differential. So what does that mean for us? So how does that have to do with the dimensional reduction? So I need to take the invariance, the dimensional reduced theory is the dimensional reduced theory means I need to take point to the Hochschild chains on my associative algebra, and I need to take the diff S1, which is just S1 invariance, which is the definition of the negative cyclic homology of the associative algebra. So now this is what we are going to attach. The dimensional reduced theory attaches the negative cyclic homology. Now, what does that look like? Well, just let's remark that when we take this dimensional reduction in general, any of these dimensional reduction, When we're taking diff S1 diff n. So in general, we've taken diff n invariance of something. This is always linear over the cohomology of B diff n. So this is the general structure. When we take Sn invariance in a homotopical setting, we get something that's cohomology, that's linear over the cohomology, the diff n equivariant cohomology of a point. So in the case of the circle, so when you do a dimensional reduction by the circle, this is linear over cochains on BS1, which is CP infinity, which is polynomials in some variable epsilon, where symmetric algebra in variable epsilon with degree of epsilon is 2. So when we do this dimensional reduction in a circle, we get something that's a family over this epsilon variable. And so we really want to think about this as a family, where at epsilon equals 0, we get the original compactified theory. And then we have sort of one more interesting value, where epsilon is non-zero. So, this process in the physics is what goes by the name of this is some version of what goes by the name the Nekrasov omega background, or epsilon deformation, or whatever. So we're going to think of this field theory. When you take a field theory and reduce it on the circle, it's really a family over this line, which is spec of polynomials in epsilon. It's a line, it's a graded line. So what we'd like to, the rough idea, what we'd like to do, to set epsilon equals 1. And what would you get if you set epsilon equals 1? Well, if you take the negative cyclic homology of, so if you look at the complex of differential forms, in this case, with the Rham differential as the differential, at epsilon equals 1, you would like to say we just get the Rham cohomology, of x. So setting epsilon equals 1 would mean just allowing this differential as part of our structure. Unfortunately, this doesn't literally make sense, and epsilon is a graded parameter. The physicists would say epsilon has dimensions of mass, so it doesn't make sense to compare it to something dimensionless. And so what would we say? So we can't take epsilon to be 1, but what we can do is we can invert epsilon. We can invert epsilon. So we can take this reduced theory, and we can tensor it over this polynomials with polynomials in epsilon inverse. We can localize epsilon. And then what we're going to get is indeed the Rham cohomology of my variety. Unfortunately, I've had to invert something of degree 2, so I only see this thing 2 periodically. I have to take this thing and base change it to polynomials in epsilon inverse, again, where the degree of epsilon is 2. So I only recovered the Rham cohomology 2 periodically this way. So this is the periodic cyclic homology of my category. But in any case, the periodic cyclic homology of a category is what you get in this picture by dimensional reduction. Dimensional reduction has a parameter in it. You set the parameter to be non-zero. You get the Rham cohomology, or negative cyclic homology. And that general construction of boundary conditions produces the Chern character in the Rham cohomology this way. OK. So I guess this is a good place to stop. And so what we'll do next time is construct some examples in dimensions 3 and 4, more complicated examples of field theory, and try to see how they relate to representation theory. Thanks.
Is it possible to take other compact groups besides the G that you looked at, as in groups which are not finite?
Yeah, absolutely. So when a physicist says topological Yang Mills or topological 2D Yang Mills, you usually think of a general compact group. And that's already a very illustrative of this phenomenon. If you look at the category representations of or let's just say a complex group, finite dimensional representation of a complex group, Well, it's a nice compactly generated category. It's certainly one dualizable. You certainly get nice invariance for one manifold. If you try to get invariance for two manifolds, you immediately run into trouble. So you have infinitely many simples. And so if you just, for example, want to calculate what you attach to a 2 torus, so 2 torus is circle cross circle. So you need the dimension of what you attach to the circle. Crossing with circle is always taking dimension. So you need the dimension of space of class functions. The dimension of space of class functions is infinite. So that theory doesn't a priori make sense for closed 2 manifolds, because well, the object is not 2 dualizable, but in some sense it sort of is, in the sense that it's an infinite sum over a set which is the set of irreducible characters, and in some sense, if you keep track of size with respect to that set, you get something well defined. So in some sense, the theory is 2 dualizable in a sense that's relative to the space of irreducible characters. So we'll try to make that a little more precise next time. So a physicist will say 2D Yang-Mills is a perfectly fine 2-dimensional field theory. It diverges on the 2 torus, but if you add some dependence on some area, then you get something that does converge. Mathematically, you'd say it's sort of a partially defined 2-dimensional field theory. And then you can make it fully defined if you keep track of, if you work relative to the Casimirs, if you keep track of the Casimirs of your representations. So that is the typical physical example. So you can already see there that when a physicist say 2-dimensional field theory, they don't mean 2 dualizable, even there. And certainly once you get to 4, none of the things physicists call 4-dimensional topological field theories are going to be 4 dualizable. And they're all going to have the same property where you have to keep track of some parameters like Casimirs. And once you keep track of the values of these parameters, then you get something that's well defined, hopefully.
Is this B differential at all related to the differential for BRST? Oh, sorry. Should I say that again?
Is it related to a BRST differential?
Is it related to a BRST quantization?
I mean, this is the... Sure. I mean, when you talk about a 2-dimensional conformal field theory, for example, well, you have a topological conformal field theory. So there's a kind of topological field theories coming from twisting supersymmetric conformal field theories. This operation, taking this epsilon S1 cohomology, this is exactly the BRST cohomology for the Virasoro algebra. So from the point of view of the conformal field theory, you have action of the Virasoro algebra on the circle. You take back BRST for the Virasoro algebra is exactly this B differential.
Could just give us some example of this Chern character, a little more detail about how to get the Chern character out of this?
Do you
want me to repeat it?
Sure.
I was wondering if you could give another, some more detail about how to get the Chern character out of this.
Well, the formal statement is just that if you give me a boundary condition in the field theory, I can now attach values to pictures like this, and that's sort of, so I get a value. Yeah, so if you want to really get or maybe I should say, you get if I give you a one dualizable boundary condition, so now it means a compact object in my category, that defines by, of course this is much more heavy machinery than you would need to define the Chern character, but if you want to use the Cobordism hypothesis with singularities to define the Chern character, you attach to this picture, define an element of the field theory on the circle. Now, this is not really the usual Chern character because that's living in differential forms. If you want to get the usual Chern character, you have to notice that this picture is S1 invariant. That this Cobordism has a natural S1 action, extending the S1 action on the circle. So the element you get an element in the theory on S1, but it's naturally S1 invariant. So it naturally gives an element of this S1 invariance, so it gives an element in cyclic homology. And this is the Chern character in cyclic homology. Now, you can use this, if you want to make this into something a little more, you can use this to prove like an Atiyah, like a Grothendieck-Riemann-Roch type formula. You can calculate the Chern character if you give a map from X to Y, and you take sheaf here, and you take derived push forward here, and you want to calculate the Chern character of push forward of V, then again, the same picture on the field theory will tell you that you have, well, we'll maybe talk about it next time, but we're trying to introduce derived loop spaces today. So I have this map from derived loop space of X to derived loop space of Y, and this Chern character of V on here defines a function, defines the derived functions on loop space of X, and you can, really, I guess it's a form, but, and you can just push it forward and get a function. So the Grothendieck-Riemann-Roch formula saying that the Chern character of the push forward is the push forward of the Chern character is, again, follows immediately from this field theory that a map from X to Y gives a domain wall between the B model for X and the B model for Y. And of course, you'll correct me that there's a Todd genus in the usual Grothendieck-Riemann-Roch, but there isn't a Todd genus in the Hochschild homology version. So the Chern character in Hochschild homology pushes forward to the Chern character of the push forward is the push forward of the Chern character. And that's exactly what this domain wall picture, you have a field theory with associated to X, the B model associated to X, the B model associated to Y, and a correspondence from X to Y. Let's say a map from X to Y. A proper map will define a one-dualizable domain wall. And so it'll give a map from the value on the circle. So Zx on the circle and Zy on the circle, you'll get a map from the field theory. And that's the push forward. So that gives you that's the Grothendieck-Riemann-Roch formula. And well, you could take S1 invariance and get the formula in cyclic homology. So that's an example of this domain wall. And again, but that's exactly what we were doing in representations. You know, character of an induced representation is exactly this Frobenius character formula. It's the same thing. You take a induced representation that you could think of it as a domain wall, and that the character of the induced representation is exactly the functoriality on the circle of the field theory.
So Todd genus gets cancelled when you use Hochschild?
Yeah. So Hochschild, Kosten, and Rosenberg is sort of bad to use, and the Todd genus it's to blame for the Todd genus somehow. If you worked with Hochschild homology or work with cyclic homology, then the functoriality is sort of the obvious functoriality. If you want to compare to, so the point is that there's if you like, there's two integration maps on differential forms. There's kind of the usual integration maps on differential forms and the integration map twisted by Todd genus. And the one twisted by Todd genus is the one that you get naturally from Hochschild homology. Hochschild homology looks like differential forms, but the natural functoriality of Hochschild homology is not, via HKR, is not the naive functoriality of differential forms. But so if you do everything on, that's what these pictures are telling you. The pictures are telling you that Grothendieck-Riemann-Roch or a Tiabat or whatever, that the functoriality is sort of the obvious functoriality in this world of Hochschild homology.